So we're going to talk about both some results from our pre-industrial control simulation that we're running for EERIE. I'm going to do that first, and then Michael's going to talk about some comparisons of the pre-industrial style simulation, so 1850 reference simulation, and the high-risk mix style 1950 reference simulation after me. I think the idea is that we each talk for 15-20 minutes, and then we'll take all the questions at the end, unless anyone has strong disagreement about that. So I've got far too many slides, so I need to keep my eye on the time. So 15 minutes.
Yeah.
So yes, so this is, I could say, a brief overview of the Met Office piControl simulations and comparison with lower resolution models. So as hopefully you know, so we're running a CMIP style simulation. So we've run 240 years of pre-industrial control with 1850 type forcing, 200 years of a PI control with 1850 constant forcings, and then historical and eventually future to 2100. All of those simulations are complete for our two lower resolution models. So we're running a typical CMIP style 130 kilometer atmosphere, 100 kilometer ocean, which I'll call LL in this case. So I've run that and actually done a couple of ensemble members for the SSP-245 and also one SSP-37 in that case. We've got a medium resolution, so about 60 kilometer atmosphere, 25 kilometer ocean. And again, that's all complete, just the one ensemble member. And then we've got our HH, which is what, of course, we're really interested in. And so that's done 240 years of spin up. And I will note, and it will kind of become clear later as well. So of that 240 years of spin up, I did 200 years with the atmosphere resolution, so 60 kilometer atmosphere, before switching to the 20 kilometer atmosphere for the last 40 years of the spin up. Now, that was probably a mistake. It obviously makes the model much faster. So for relatively few processors, we can run the at 2 years a day. At best, on a lot of processors, I can get our model to run at about 0.7, 0.75 years a day for the HH. And the atmosphere is a big chunk of that cost. So I thought it would make it faster, but wouldn't make too much difference to run with the lower resolution atmosphere for part of the spin up. It turns out that was not true, as you'll see later. And then, so for this model, the historical is partway through, so it's in about 1967 at the moment. So it's got 45 years or so to go, and we're hoping that that will be complete by May this year. And then the future part of the simulation will hopefully be done on our new supercomputer, which will, the current supercomputer finishes at the end of May. So it's a bit of a race whether the model finishes before the supercomputer finishes, which just makes things a bit more interesting. So just some very broad features of the model. So these are kind of low, middle, and high resolutions, and these are quote-unquote biases. So this is using Hist in kind of 1870 to 1900, and these are pre-industrial simulations, so 1850. It's kind of not perfect bias. But in terms of those differences, as you might expect from a low-resolution model, so you have your typical tropical cold tongue, you've got your Gulf Stream in the wrong position, you've got some warm spots in the upwelling regions, cold in the tropical Pacific. So you've got all of your favorite biases. As we increase the resolution to middle and high, and I think you could certainly say for the high resolution, if you focus on tropics to maybe mid latitudes, those biases are really low. The model looks really good in the tropics to kind of mid latitudes. So you've got at the bottom here is the higher resolution minus the lower resolutions. This is where the differences are. So you remove the tropical cold bias, You cool down some of those warm upwelling regions. You get the Gulf Stream in more or less the right position. But you can see some of those at the expense of warming the higher latitudes, so kind of get really quite a warm Southern Ocean and kind of warming up into the North Atlantic and possibly up into the Arctic. And then that is at least part of the reason why the sea ice is not so good. So this is again all the way from the start of the spin up, and then the dashed line is 240 years, so the end of the spin up and into the 200 years of PI control. Here the low is blue, the middle is red, and the high is green. And you can see from the Arctic, so the stars here are, so the grey line is Hadist observations, so obviously kind of present day, and the stars here are kind of the winter and summer typical value stroke range. So you can see here that the green, so the high resolution, looks okay in the spin up, but I think possibly it's not the resolution, increasing the resolution in the atmosphere per se, because the polynya in the Southern Ocean, which the Southern Ocean is over here, I'll talk about that in a minute. But it looks like for the high resolution, gradually the sea ice erodes in this PI control part, which may be linked to the AMOC, meridional overturning circulation, which I'll talk about a bit later. But anyway, so you can see the sea ice in the Arctic is considerably lower than these lower resolutions and considerably lower than present day observations. And ditto, the summer value is also very low. The Southern Hemisphere, you can see, is kind of even worse. Again, the grey is kind of quote-unquote observations with some idea of the range of the observations with the stars. And you can see again that the low resolution, kind of ticks along and looks okay. The red, the medium resolution, does some slightly strange things, and the high resolution, actually somewhat before I switched the resolution from medium to high in the high resolution, a polynya opened in the Southern Ocean, which so the polynya kind of wipes out a lot of the Southern Ocean ice, because it starts a convection, and in the Southern Ocean it's warmer and saltier underneath and cold and fresh at the top. And so once you get through that cold and fresh bit at the surface, you entrain warm salty water from below, and then that melts the sea ice considerably. And so you can see this event, the sea ice rapidly declines in the high resolution model, and then so it declines kind of gradually, but that biggest decline is in the early phase, which is a combination of the polynya and then probably the higher resolution atmosphere definitely doesn't help in that recovery. So the Southern Hemisphere, the sea ice is a real issue for this model. And you can see in particular in the Weddell Sea how that happens, and the Weddell Sea sea ice gets very low, both in winter and summer. So you may have seen this before, so thanks to Rohit for giving me this code. So it's following the Streffing et al. Paper. So this is trying to give you a very broad overview of metrics. So probably it's a little bit small, but on the y-axis is a bunch of different metrics. So sea ice concentration, surface air temperature, cloud, precip, blah, blah, blah. So the kind of top ones are more like atmosphere, sea ice and atmosphere. And then the bottom ones are ocean related. And then along the bottom are a bunch of regions and seasons. So again, a kind of bunch of different aspects. And so the darker the green means that model is better than much of the CNIP6 archive. Although note I'm comparing the CNIP6 historical simulations with the PI control here. So again, it's not a perfect comparison. But the darker the colors, then it's a really good model compared to the CNIP6 archive. The darker the red means it's well down, not doing very well compared to CNIP. So you think the LL model does okay. There are some things that maybe doesn't do terribly well, but it does a pretty good job. There's a mix of dark greens and dark reds. And I think you can kind of see overall that the HH actually looks pretty good as well. There are lots of dark greens, particularly in the ocean aspects. You can see some reds, so over here is Antarctic aspects. So you can definitely see there are some issues with the Antarctic, which would make sense with having not much sea ice. And you can maybe see some issues in the Arctic region as well. But overall, again, just kind of overall, it seems to be doing a reasonably good job. I'll kind of have to skip through these, but I have got then metrics of time depth changes from the initial conditions or from the first year of the model simulations, where you can kind of track through all the way from the start of the spin-up to 240 years of the spin-up and the PI control, how the global ocean in terms of temperature on the left and salinity on the right, how those evolve in the low, middle, and high resolution models. And so you can see certainly that the high resolution model is doing something rather different in terms of temperature. It certainly ends up in a rather different place. And the salinity doesn't get nearly as fresh in the high resolution model. And in the Atlantic, perhaps is even more stark that the state that you end up in with the high resolution is rather different from the low resolution, both in temperature to some extent and in salinity to quite a large extent, where you get this increase in salinity in the thermocline at low resolution, which is not nearly as bad or in the same place, at least at high resolution. We've kind of got metrics for that. There's a few other things, so you can look a bit at variability. So this is the sea surface height variance from, again, the low, middle, and high resolution model and from Aviso. And you can see as you increase the resolution, as we expect and as we know, we begin to pick out the boundary currents in a much better way. The Gulf Stream looks like it's in more or less the right place. Horatio kind of extends further into the Pacific. You see all your favorite features in the Southern Ocean as well. Some of those may be becoming more evident in the quarter degree, but certainly the Gulf Stream is still a bit underpowered and doesn't have the peaks in energy in the right place. In terms of the Atlantic meridional overturning circulation, so the AMOC kind of volume transport is in the top and the heat transport is at the bottom. And so here again, this is from the start of the spin up through the 240 years of spin up and 200 years of PI control. And you can see here how the light green was with the medium resolution atmosphere, and then switching to the high resolution atmosphere, the AMOC went from maybe 15 spare-drops to maybe 20 spare-drops in doing that switch. So that's where I think that you could definitely interpret that as being not the right thing to do, because effectively you're changing the mean state of the atmosphere, which is going to evolve globally through the rest of the ocean and the rest of the climate for many years of the PI control. So there are certainly some metrics that are only beginning to look like they're back in balance towards the end of the 200-year PI control. But that at least shows for our model that switching the atmosphere from 60 to 20 kilometers makes a huge difference to the AMOC strength. And you could definitely say that for the high resolution, the AMOC strength is too high. So here's the range from rapid, and these are calculated consistently with rapid, so they really are comparable. It's a bit high in terms of the volume transport, and it's probably a little bit high in terms of the heat transport, but it's adjacent to the northward heat transport from the observations. The medium resolution is also more or less consistent with the present day heat transport, but the low resolution model, although the volume transport looks good in the low resolution model, the heat transport is definitely outside of the range of the present day heat transport. And I think you can argue for the Atlantic whether it's the volume transport or the heat transport that's really important, but I think the heat transport is certainly equally as important, that we should bear in mind. I did for time. So I need to speed up. So I've also been using the PCMDI metrics package to look at some of the mean state stuff, and also it can do ENSO and other aspects of variability. So there's some for those three different models. Again, I've done some metrics of ENSO related things comparing to the CNRS models. One of the expansions of one of those biases is the precipitation seasonal cycle in the tropical Pacific. And this in particular looks at the ITCZ from observations, low, middle, and high resolution. And actually you can see in this case, the high resolution model, you can see has rather more of a ITCZ signal than the low resolution model. It's perhaps not the most severe ITCZ you've ever seen, but definitely it gets stronger with resolution in this case. Other aspects of ENSO look pretty good. And I think I definitely am going to encourage people within the project and certainly within the new HiResMIP2 to make use of PMP for the range of metrics that it does. It can generate basically those colors, which you can save as a JSON file and then just plot against your model and do the new calculations with your model. And also noting that PMP will form part of the CMIT-REF, so the standard reference package. So I think it's good to kind of be on board and to be starting to use that. I confess I only managed to do this on Friday, but this was mostly for our African colleagues, because I know they mentioned that the Indian Ocean dipole is really important for aspects of climate over Africa. So I've only just managed to do the monthly time series from the piControl, and I need to fit some kind of smoothed time series to look at the variability, but that's kind of ongoing work. But the IOD, I think, is something we should also think about. This has been presented before, so this is probably the first EERIE SES was on the coupling to show that at the mesoscale, so at the high pass filtered scale, as you go from low to middle to high resolution, the kind of coupling strength, so this SST wind speed coupling looks extremely different in the high resolution model and begins to look like observations, although there's still areas in the Atlantic and elsewhere where it's not perfect. And I still wonder out loud whether some of improving these coupling biases will improve our signal to noise and other aspects of the models that are clear from seasonal forecasting with the middle resolution that our seasonal forecast uses that does not get good signal to noise. But you can see big areas of particularly the Atlantic where that coupling is just not the right sign. We've done some, with Michael, just some brief calculations of climate sensitivity, and we only have 30 years of the 4x CO2 run at high resolution, but there's indications that probably because there's so much less sea ice, the climate sensitivity is lower because of those smaller feedbacks, and that's something we'll do. A brief look forward, so the historical surface air temperature time series, the green is kind of how far the historical simulation has got so far at high resolution. But you can see all three resolutions do a pretty nice job of the historical to about 2000, where their high climate sensitivity mean they warm really rapidly. But until then, they do a really nice job of that. And the AMOC kind of going into the future as well. So as we would expect, the lower resolution models, the AMOC declines kind of from the present day into the future, and we will see how the high resolution model does in that respect as well. And probably not, running out of time really, but typically this was working, but thanks to Aaron and Emma, so we have got some movies of the marine heat waves, which are typically not going to work right now. So, but ask me later, and I can try and play those. But the marine heat waves are looking quite interesting as well. Oh, there we go. And the high resolution model, the characteristics of the marine heat waves look quite promisingly similar to the ESA observations. And then really just to advertise that it's not just our models that we have to do our analysis with. So the Mesoclip, the CSM high resolution, that data is now available if you go to the Mesoclip link. Not all of these simulations are available, but certainly the 10-member 1920 to 2100 data is available. And this could be an amazing resource to compare with our EERIE simulations that actually have multi-member ensembles. They do the tropical Pacific trends in a really nice way. So I really encourage people to look at the data sets that are available there and think about using them as well. And that is me done. Thank you very much. I will pass over to Michael.
Yeah, so I'll be talking about something a little bit different, about comparing the impact of using different experiment protocols on the interpretation of the control in historical simulations, comparing when you use the CMIP style controls with the high-res MIP style simulations. Yeah, so funding. Yeah, so in order to participate in CMIP, modeling centers are required to run the baseline DEC simulations, which are the 1850 control, the 1% CO2, abrupt 4 times CO2, and the historical AMIP runs. We're focusing on the 1850 control in this talk and the effect of that. So performing these simulations from an 1850 baseline is really expensive for high resolution models. So the high-res MIP decided to use a different experimental protocol based on the 1950 conditions and using a shorter spin-up. However, because of this, it's not quite clear how the higher resolution models really compare to the rest of the CMIP models, as not only are the resolutions different, the sort of baseline forcings and spin-up lengths are also different. So this study is just trying to quantify that a bit better to understand what we can compare and what we can't compare, and how we can go forward to better link with CMIP.
Excuse me, Michael. We are seeing
the
presenter view. Can you do something?
Oh, you're seeing presenter view.
So sorry.
Okay. Is that better? Okay. Okay, yeah, I think that works. Yep, and this is just a short summary of the previous slide, really, that the Met Office EERIE models are running the CMIP style runs. But the other European models would be using the high-res MIP protocol, just to keep that in mind. And this is a kind of diagram showing the key differences between the two protocols. So in high-res MIP, the spin-up is about 50 years with a 100-year control based on constant 1950 forcing. And in CMIP, the spin-up is often multi-centennial. So it will be a lot more stable than the high-res MIP control simulations, and they also run the control for 500 plus years. And another important difference is that in high-res MIP, the aerosol is high-res MIP models tend to use the EERIE prognostic. No, not prognostic. There's prescribed aerosol. Sorry, I'm getting a bit confused. Yes, use the prescribed EERIE forcings, but in CMIP there's no such constraint, and each modeling center can choose their own aerosol schemes. And in the case of the Hadja model that we're looking at, it's a GLOMAP, which is quite a complicated aerosol scheme with indirect effects, and that would be important later on. The first result is just comparing the control simulation of the piControl and the high resolution control of the. One other thing to note is that for CMIP 6 and for high-res MIP, the Met Office model is the only one that ran both high-res MIP and CMIP with the same configuration. I think all other modeling centers use slightly different models, so you can't really do this comparison. I think CSM might also have done this, but I have not looked into that yet. So that's why I'm looking at the Met Office model. And yes, so the first result is the control simulation comparing the PI control with the high-res MIP control. And the blue line is the high-res MIP control based on the 1950 forcing, and the black line is the PI control. And yeah, it's kind of surprising, but the 1950 control is about 1 Kelvin cooler than the 1850 control at the start. And the first 400 years, there's a stronger warming trend in the 1950 control, but it kind of stabilizes later on. Yeah, so it's a bit of a surprise why the 1950 control is quite a lot cooler than the PI control. And just to say, I'm only showing results for the low resolution model here, low, but results for the medium resolution are quite similar as well. Just removed it for simplicity. So looking into the historical simulation, on the left-hand side is the absolute value of the global surface air temperature. Again, black for the CMIP 1850 historical and blue for the 1950 historical. That's using high-res MIP, and red is the ERA 5 data observations. And again, yeah, the blue line is about 2 Kelvin cooler than the black line. However, if you look at anomalies defined with respect to the control, so if you remove the control, the time series are a lot more comparable. The Hist-1950 is only about 0.2 Kelvin warmer, and that could just be to do with the ensemble spread. Yeah, so it appears that although the absolute values and the mean states are quite different between the high-res MIP and CMIP runs, when you take the anomalies, the time series look a lot more comparable. So we can dig a little deeper into this and look at the spatial pattern to see how the rate of warming in different regions look like. So these spatial patterns are defined by the mean of the last 30 years minus the first 30 years. So basically, this 3 decades minus these 3 decades here, and the spatial pattern of that. So yeah, so on the top left is the ERA 5, the observed pattern. In the top middle is the 1850. It's a change in the surface air temperature based on the 1850 run, and on the right is based on the 1950 control. And in the middle row is the difference of these temperature change patterns in the models compared to the observations. So the red area means that the simulations are warming faster than the observations. So this is especially stark in the 1950 run. The kind of North Atlantic warming hole that's seen in the observation isn't really present. Warms a lot quicker, especially, and also in the sea ice regions as well. And the bottom right panel shows the difference between the runs based on 1950 and 1850. You can see that the runs based on 1950, the rate of warming is quite a bit faster, especially over the North Atlantic. So that's saying this trend is quite a bit steeper than the black line in the North Atlantic basin. So although the global mean time series looks more comparable, for the anomalies, there are actually quite a lot of differences in terms of the spatial pattern, like the regions which are warming faster. So all of this is to say that the 1950 runs compared to the 1850 runs are quite different despite using the same model. Yeah, and the reason for this is we think largely due to the aerosol, the fact that there's the high-res MIP runs uses a prescribed EC aerosol, and the CMIP runs use the prognostic aerosols. So it is shown in this figure, which is the top of atmosphere outgoing shortwave. So the red lines are the simulations that I've been showing, the GC 3.1. The dark line is the PI control, and the lighter line is the 1950 high-res MIP control. And the blue lines here are additional experiments that we have ran with the GC5 EERIE model, so the version that's used for EERIE. And for this version, we know for sure that the aerosols are exactly the same in both the 1850 and 1950 controls. So we've controlled for aerosols effectively. And the difference between the blue lines and the red lines are, well, quite big. So the top right panel shows the pattern of POA shortwave in a GC5 EERIE run. So basically the difference between the two blue lines, this arrow, is the pattern here, and then the red line, the difference between the red lines is the pattern at the bottom right. And basically what the pattern at the top right shows is the pattern you would expect for the 1850 and 1950 POA outgoing shortwave to look like. You see this sort of northern hemispheric pattern centered around the US and Europe, where you have SO2 emissions from the Industrial Revolution. This is the kind of pattern you'd expect to see in terms of how the aerosols should look like in 1950 compared to 1850. However, in GC 3.1, that pattern isn't there. There's a blanket sort of much more outgoing shortwave in the 1850 run, in the 1950 run, sorry. So this explains why the 1950 run is a lot cooler, despite, should be higher CO2 levels. It's because the aerosol forcing is different. So once you account for this in the GC5 EERIE runs, so again, the blue line is the 1950 control and the black line is the 1850 control. They are much more similar. There is still the impact of the shorter spin-up length, so there's some drift in the first period of the control, but about 300 years in, it's a lot more comparable to the 1850 control. So accounting for aerosol, the next things that we're going to look at is to quantify the effect of the spin up and the forcing, which is what we originally set out to do until we found out that the aerosol was really important. So we're running some new simulations with the GC5 EERIE model to quantify the effect of spin up a length and the difference in forcings. And we kind of have begun doing that with, so the red line here shows what the 1950 control looks like if the ocean is fully spun up, which is what you expect. It's slightly warmer than the PI control. And I guess the difference between the red and blue line shows you the impact of the spin up length. And that's all I've got at the moment. But looking forward a bit, for high-res MIP2, there are 5 key differences from high-res MIP1. But the most important one in the context of this talk is that high-res MIP2 allows the use of any aerosol scheme, so no longer prescribes the EC aerosols. So for high-res MIP2 to better compare with CMIP7, it would probably be best if they use the exact same aerosol schemes, because otherwise, the means they can be extremely different. So my conclusions are that the aerosol matters quite a lot in determining the mean states and actually how you interpret the control in historical simulations. further simulations are being done to better quantify the impacts of the forcing and spin-up length. And yeah, I'm just repeating myself now, sorry. Yeah, just some additional comment is that one control is not superior to another. They are different, and they're things that can't be easily compared. You know, they might serve different purposes. The 1850 control gives you a better sense of what internal variability might look like in the models, but we don't really know what the 1850 climate looks like. The shorter 1950 control might have some drift because there's some CO2 in the atmosphere already in 1950, so if you ran it for too long, it will drift. But you might be able to start from a more realistic state that we have observations of. And the other thing to point out is that some variables might be more comparable in the two control runs. I looked at surface temperature only, but Benoit's results from before show that sea surface height might be more comparable. So yeah, so some further work to quantify what can and can't be compared. And that's it from me.
Thank you very much, Michael. Jin Song, you want to start with the questions?
Is that only the mean state regarding the aerosol, so that if you consider the historical run relative to the control, then you get rid of the mean state, then everything is fine?
Yes, I did look at that. Yeah. So if you average across the world, yes, the global mean surface temperature anomaly time series is a lot more comparable. But if you look at regions separately, which is what the patterns of surface temperature changes were, there were actually large differences, especially in the North Atlantic and the Arctic, between the two runs. So it's not just a mean state thing. There are regional differences as well.
Thank you. And perhaps I have another question, Michael. So you say that these prescribed aerosols were used in IRES-MIP1.
Yeah.
Was the effect similar in all models? I mean, did somebody notice that all the IRES-MIP1 models were cold, or did it affect each model in a different way? So you cannot really tell anything.
I think it will affect models in different ways, because this also depends on what the aerosol scheme was used for the CMIP model. In this case, GLOMAP for the HADGEM model is quite sensitive. It has the indirect effects and so on. So it's quite a sensitive aerosol scheme. So other modeling centers using other aerosol schemes might find a difference. As far as I'm aware, no other modeling centers use the exact same models between CMIP and HIRES-MIP, so the same comparison can't really be done in the same way, except for maybe the CESM model. But I have not looked into that model yet. But I can't remember, Malcolm, do you remember if there's a systematic difference in SST mean state between HIRES-MIP?
Yeah, I also don't remember anyone. I don't remember ever seeing that, at least. I mean, obviously, within HIRES-MIP, we had our low and high resolution, and I guess, again, that was probably the main comparison rather than comparing the models to observations. So I don't remember anyone suggesting that there was a systematic cold bias in HIRES-MIP simulations, no. I'm happy to be contradicted by anyone.
Actually, I have
Yes, somebody.
I have a few more questions to mark on. If you have these three different resolutions in the atmosphere, are you changing the parameterization?
In the atmosphere, very few. There's about 2, 3 fairly minor parameters that we have to change, as well as the time step and the things that you definitely have to change. I mean, the ocean, obviously going from a 1 degree ocean to a 1/12 ocean, we changed the things that you would expect to change. With EERIE, actually, we have Jetman-Williams switched on across all resolutions, but with a strong quote-unquote scale awareness. So it scales down to be very small at the highest resolution. But the GC5, we decided to actually keep it switched on across the resolutions. There might be one or two other things that typically changed. I mean, we change the things that typically get changed from an Orca 1 to an Orca 12th degree simulation. Yeah.
So can I summarize to say that you're trying to use resolution aware type of thing so that you can change as little as possible for the different resolutions?
I mean, for the atmosphere, we always we don't have we don't know how to tune the high resolution atmosphere, so there are very few changes we make because we don't know how to make it better, so we just stick everything as close as we can. I mean, the convection scheme in the atmosphere here is not the scale aware COMORT, but it is the initial version of the atmosphere convection parameterization that is being worked on to become a scale aware. So that's kind of the hope for the future, is that we'll be able to have a more scale aware parameterization in the atmosphere. And in the ocean, yeah, so I mean, I think my ocean colleagues definitely don't call this version of Jetman-Williams scale aware, but it is trying to kind of ramp down how important it is from low resolution, where it's obviously completely essential, to high resolution, where it's not, doesn't need to be very strong. But if you want to be consistent, I mean, I confess I don't like at a given resolution switching things off, because, well, why that resolution? So we would like to get some of these things a bit more scale aware, and systematically decline with resolution rather than just switching off at some point. But we're not there yet, but we're hoping to get there.
Okay, and then the other thing, when you switch for the spin up from the 60 to 20 kilometer atmosphere, you see the jump, and you just keep then going, or you repeat your spin up?
No, so for the 240-year spin up, 200 years was with the 60 kilometer atmosphere, and then 40 years was with the 20 kilometer. I mean, noting that spin up simulation started at the end of 2022, and the simulation is now, 3/4 of the way through the historical, and that's the same simulation. That's one simulation. So I was trying to save time by doing 200 years of the spin up with a cheaper model, and then 40 years, hoping it wouldn't be that different, and then doing 200 years of the piControl. But certainly, kind of looking back, yes, rather than doing 40 years with the higher resolution atmosphere in the spin up, that should have been a lot longer. But then the simulations were for EERIE, and obviously, they're already delayed from what I was hoping to deliver for EERIE. So it's been a very long time. I know that we've all struggled with our simulations, but I knew this would take a very long time, and it's taken slightly longer than the very long time I was expecting. So that was the lower resolution atmosphere, was just to try and cheat a bit and save some time, but probably based on the GFDL recent paper as well, that was probably a mistake. But I didn't know any better at that point. So.
Thank you.
May I ask another?
Because Matthias raised his hand.
Yes.
So maybe Matthias.
I will ask it later.
Yeah. Okay. So Matthias.
Yes, I just had two questions. First, one sec. You showed the SAT evolution, and you said the warming, like they followed the observations quite closely, and then they sped up in the last years. You sent me some time series from the AMAP runs, and that I followed quite closely, at least from the medium resolution one. I don't know if you finished the high resolution AMIP by now. And I thought it was very interesting that it followed so much closer to ERA 5 than our simulations in the last 10 years. So it's interesting that this is so different in the coupled runs.
I mean, so obviously the AMIP simulation, the SSTs are constrained, and it's a good question, because you can run AMIP style simulations to get some feeling for the feedback, which kind of relates to climate sensitivity. But yeah, in our model, we seem to have a balance in terms of the aerosol, the sensitivity to the aerosol and the sensitivity to the greenhouse gases, I guess. And yeah, for much of the historical, those balance quite nicely. But certainly in the coupled model, yeah, at the end, the greenhouse gases really win, and you get a strong warming. I don't know whether, as you say, the difference between the AMIP and the coupled, that maybe there's a feedback via the ocean in that respect. Yeah, it's an interesting point.
Yeah,
the high resolution AMIP is still stuck at 2014, because I'm still waiting for someone to give me the code to do the future aerosol forcing. But I need to poke them again, as I poke them every month. But yeah.
Yeah, just looking at the time series, I had been wondering whether your interactive aerosol scheme made that difference. I mean, it was just one time series, so I don't know, but that was a thought I had. Do you have actually the aerosols or aerosol fields, so we could try and compare aerosol forcings or something, effective forcings or something?
I think some, definitely some aerosol diagnostics come out. Yeah,
that would also be interesting.
I don't look at, but yeah.
Yeah, cool, thanks. And just one other question, because you showed that the 1950 control in the beginning was a lot cooler than the 1850 control, and I was wondering, what does it mean in the beginning in the terms of this PI control? What do they start from a different initial state? What does it mean, the initial state here?
Oh yeah, sorry. No, they do start from the same initial state, which is EN4. But I guess that's the difference in the spin-up length. Now the PI control at the start of the control has already had 400 years of spin-up. But
right, so it's after the spin-up.
Yeah, so when you couple to the EN4, the model cools a lot and recovers. So I'm talking about that bit. And I think that bit does matter, because that's where you branch off to do your historical as well for the 1950 control. So that difference there is quite important, I think.
Have you looked at like the time evolution of how this cools over those 400 years? Is that very quick, or is it more like a continuous cooling?
I guess my time depth plots give you some indication in terms of the ocean, at least how that it gets very cool at near the first few hundred meters of the ocean, and then there's maybe deeper down, there's some warming and some cooling. So yeah, I guess those might give you some indication.
No, but you're right. I need to look at how the drift looks like in the ocean interior, because that might add a different time scale to it as well.
Yeah, even in the surface, it would be. I was just curious: what time scales is this happening? Very cool.
Yeah. But the GFDL paper that's out in preprint, if you haven't seen it, does suggest that going to a higher resolution ocean, the spin up gets much shorter, because the communication between between the deeper ocean and the surface is mediated in a different way from the lower resolution. So the evolution is different. The time scale is different.
Thank you.
Well, Malcolm, yes, I would be interested by a preprint of this GFDL paper, if you have it, if you can send it around.
Is that?
Yeah. It was GMD or James, I think, but yeah, there's two papers that are in preprint.
Okay. Jin-Sung, you had another question?
Yeah, I have another question. Just wondering whether I read your diagram correctly about the trend. It looks actually like as if it equilibrated pretty fast. That at the I think that's the time and depth that does not changing too much after, I couldn't remember the axis. Is that correct to say the drift is actually pretty small? It's very, if that is the case, that will indicate that we don't need too long spin up.
So that one's to me on the time depth plots. Yeah. So it's true that initially the kind of near surface cooling and the subsurface warming, is maybe obvious, or maybe peaks in the first 100 years or so. But then there are kind of deeper ocean things that change more slowly. And the vertical scale that I had really exaggerated the first few 100 meters of the ocean. So I suspect if you did the vertical scale proportional to the depth, the thickness of the layers, then perhaps that figure would look a little bit different. But yeah, I mean, the near surface kind of cools quite strongly initially and then pretty much stays the same.
Yes.
But the deep ocean has certainly some longer time evolution. I guess that's what you'd expect.
Okay.
Are there other questions in the audience? No, I don't think so. And the hour is almost up. So I have been told that I have to advertise for your presentation, Matthias. You are doing the next science hour for EERIE, right? Yeah, so that will be the 14th of April at 2 p.m. And you will talk about the atmospheric imprint of ocean eddies in high-resolution atmosphere-only simulations. So everybody is welcome to join. And thank you very much, Michael and Malcolm. And I'm sure we will talk about this again at EERIE meetings.